Welcome to Disruption Dialogues Podcast Season 2. Listen to the influential leaders and trailblazers from around the world as they share invaluable insights to navigating the fifth industrial revolution.
Hello and welcome to another episode of Disruption Dialogues Season 2. I'm Sarwant Singh, President and Chief Commercial Officer at Markets and Markets. Today we'll be talking about the future of semiconductors. Semiconductors power everything from our personal electronic devices to large data centers, from the cars we drive to the huge potential of AI, making this industry more critical than ever. We in Markets and Markets expect that the semiconductor industry will grow to over $1 trillion from its current size of $600 billion by end of this decade. Today, we hope to cover various topics, including semiconductor sovereignty, supply chain challenges, opportunities and implications in the UK and Europe, and the impact of AI and sustainability to the industry. To enable this today, I'm in conversation with Andy Sellers, Chief Business Development Officer from Compound Semiconductor Applications Catapult. Andy is a well-known industry thought leader in the semiconductor space here in the UK. And one could even say he's the brain and architect behind the UK government's vision and strategy to set up the semiconductor catapult and industry here in the UK. Thank you, Andy, for joining us today.
Thank you, Sarwant. A very kind introduction. I look forward to our discussion on semiconductors.
Thank you, Andy. So, Andy, the first question I have for you is the semiconductor industry today is going through several seismic shifts. One of the most talked about questions is the question of semiconductor sovereignty. And we're seeing, with the Taiwan and South Korea accounting for about 75% of the global semiconductor manufacturing. We're seeing US CHIPS Act, suggesting about $53 billion in funding and incentives. EU following that up. China has, come up with its own set of tax incentives and some restrictions. Likewise, we see that with South Korea. So I'm keen to hear your thoughts on how these initiatives will shape the overall semiconductor industry over the next decade.
That's a great opening question. I think, Sarwant, it's probably worth reflecting on how we got to where we are at the moment. So if we kind of roll the clock back maybe to the 1980s, actually, there was a lot of production around the world. There were a lot of silicon fabs in the US, a lot of silicon fabs in Europe, and effectively the Far East took some very long-term strategic decisions to become world eminent in semiconductor production. And effectively what has happened is that they have led the wave of being able to fabricate the cutting edge silicon semiconductors. Now, the economics means that you don't need multiple fabs to do this. You really need one super fab. And what we've seen is the market economics has favored a single super fab in Taiwan and South Korea doing the vast majority of the cutting edge semiconductors. And as a result, other parts of the globe have specialized in other parts of the value chain. So this has kind of been a move of globalization. I think we can probably even trace it back to around about maybe the fall of the Berlin Wall, as we were seeing an opening up of democracy and an opening up of globalization. Different countries have started to specialize in different parts of the supply chain. And it's actually, in some ways, specialization is a good thing. So Taiwan and South Korea have specialized in the fabrication of cutting edge silicon devices. The UK and the US has specialized in design. The Netherlands has specialized in the tools to produce the devices. So different countries have specialized in different areas. And in some ways, specialization is a good thing. It's driven up productivity, it's driven up innovation, it's driven down costs, but at the expense of complex supply chains. And we probably weren't really aware of exactly how complex those supply chains were until we hit the pandemic in 2020. And all of a sudden, companies and sectors like the automotive sector realized that they couldn't complete a $30,000 vehicle if they didn't have a $10 chip. And it was the traceability of that chip and the kind of market movements that kind of really shone a light on the complexity of supply chains. And what we're now seeing is a response to that. So you pointed out the US investing $53 billion in the US CHIPS Act, the EU investing 43 billion euros. There's some other investments as well. I mean, India is looking to invest 10 billion in semiconductors. I understand China is looking at $143 billion investment in semiconductors. So we are starting to see countries kind of trying to redress the complexity of the supply chain and trying to reshore and boost their own sovereignty, their own sovereign capability. So that seems to be in a response to how we've got to where we are. Now, your question was about sovereignty, and I think it's actually probably fair to say that even with these interventions, it's very unlikely that one country will have a complete supply chain from end to end to do the entire semiconductor and product development. So I think there's going to be a shift away from this globalization that we've seen for the last 40 years. We're now starting to see a shift back towards more national capabilities. But it's very unlikely that any one country will have a complete supply chain as a result of that, I would think.
Thank you, Andy. Totally agree. And maybe just to follow on to that. So what does this mean for Europe and the UK? We've been a bit slow here in Europe and UK to respond, and we've lost that edge to other regions. So when you say, some of this industry will come back, so what does it mean to us here?
Yeah, I think, okay, so I think firstly, I think what we need to look at is there are broadly three types of semiconductors. There are silicon semiconductors, there are compound semiconductors, and there's some emerging semiconductors. So the landscape is actually quite complex. And the majority of the investments which are going on in the US and the EU tend to be targeting silicon production. I've got some statistics here, and actually the offshoring, if we look back to sort of the late 1990s, in 1998, Europe had 22% of the global silicon production, and that's fallen to about 9% in 2017. And similarly, in 1990, the US had 37% of the global silicon production, and that's fallen to 12% in 2022. So there's been a progressive shift away from Europe and the US, as I kind of indicated earlier, predominantly towards Taiwan and South Korea. And these interventions are about redressing that balance. Now, predominantly the investments which are going on in Europe and the EU are looking at trying to repatriate, on the whole, trying to repatriate silicon production. And I think what that means for the Europe and what that means for the UK could be subtly different things. And I think where we need to be careful, where we need to be clever, if you like, is in the UK in particular, we need to look at where we have specific strengths. And rather than trying to duplicate what is going on globally, when you have subsidies going into an industry, they distort the market. And I think one of the areas of potentially of concern is when you have one subsidy versus another subsidy, it becomes a subsidy race. And I think the UK has to be very careful not to get into a subsidy race, to be very careful about where we have strategic competitive advantage in our technologies and our markets, and to really sort of apply that logic and see where we fit in. Now, I think specifically where we have identified strengths in the UK is in chip design, it's in research and development, and it's in compound semiconductors. So I think the bit for the UK is to try and maximise our value in those three areas, because they don't compete with what is going on broadly in the larger ecosystem, and they will complement what's going on. And as I said earlier, I don't think any one country will ever have an entire sovereign supply chain. So by the UK being clever and being selective, I think we can have a better relationship with the other investments that are going on.
Thank you, Andy. I totally agree. I think we have to be selective. We have to decide, where we have an edge and where we compete and where we add value. Moving on, you mentioned earlier, we saw the semiconductor industry over the last 3 years gone from a feast to a famine situation. We saw how there was shortage of cars, prices went up, and suddenly we now seem to have a glut. Do you think this is cyclical, and will it just even out over time, or do you think this will continue for a while?
I think the semiconductor industry has been notoriously cyclical since its early days in the 1970s. And I think some of the reasons for that are the time lag between identifying the market opportunity and putting in the fabrication capability to address that market opportunity. So, for example, at year zero, if you spot a massive market and you say we're going to address that market, it might take 5 years to design and commission a semiconductor fab to come on stream, and then for that fab to become high yield and get its yield improvement up to address that market. Now, that time lag effectively means that by the time you've got into that market space, the market dynamics have changed. And so I think this is some of the fundamental reasons behind the cyclicality of the market, if you like. So it has been notoriously cyclical, and I think in particular, in the memory market it's been more cyclical than in other parts of the semiconductor market. what tends, if you look at sort of control, if you look at sort of control systems, and this is what it is, it's a control system. When you're trying to even out a control system, you're looking at how responsive you are, and it's if you're not responsive, then that's when you get cyclical activity. And what particularly happened during the pandemic is we had a disturbance, we had a step change, and control systems quite often responded different ways to step changes. And this in this particular instance, how it responded to a step change was to create a shortage in the short term, which has, as it's panned out, has led to a glut in the medium term. So I think this particular, what happened in the beginning of the pandemic is all of a sudden people weren't traveling so much, they were working from home, their need for vehicles went down, their need for communication devices, mobile phones, laptops went up. The semiconductor industry shifted towards addressing those mobile devices at the expense of not addressing the automotive industry. As we came out of that situation, the supply chains for the automotive industry had dried up. So there was a step change in demand, if you like, which kind of, as it rippled through the industry, created a shortage of particular chips for the automotive industry. Will we continue to see cycles going forward? I suspect it is inherently a cyclical industry, as I say, because of the amount of time it takes between making a decision to invest in semiconductor production, designing the fab and bringing the fab on stream. So I think there probably will be elements of that going forward.
Thank you, Andy. And maybe a side question, Andy, that just made me think, we've seen in the semiconductor industry, companies like Tesla, Apple, sort of getting themselves into it. If you look at the auto industry, where I spend a lot of my time, they're notorious for owning the supply chain. So do you think like car companies and the fact that we will need so many chips in the car in the future, and we will need advanced chips for autonomous and connected vehicles, should they become manufacturers of chips, or are they better off relying on experts to buy the chips from?
Yeah, that's a very interesting question. So I think and you've highlighted two different approaches to managing your software supply chain. So Apple and similar companies take a very deep interest in the next generation of chips that are coming through, and the next generation of fabrication technology. Are we moving from 5 nanometer down to 3 nanometer? What more can we do on 3 nanometer that we couldn't do on 5 nanometer? I think historically, the automotive industry has paid less attention to this side. And I think it's probably fair to say that quite often the automotive industry works on a just-in-time supply chain. They want to minimize their inventory of components in the supply chain. And I think they've probably taken, as I said, they're probably sort of taking less of a deep interest into the actual second and third tier in the supply chains. Now, if they're going to be responsive, and also what we're starting to see now really is that the automotive industry is migrating from being historically more of a mechanical manufacturing and design process to being more of an electronic and high tech. Vehicles, the amount of tech going into cars, from autonomous and navigation systems and what have you, they are moving in the same direction as the high-tech industry, like mobile phones and laptops and tablets. So I suspect that the automotive industry is going to have to take more of a closer interest in the semiconductor industry and the semiconductor supply chains. And there is some argument. I mean, I hear what you're saying about, Apple itself has taken a great interest in being able to design its own processors. They've moved into the design space. I suspect they won't get into the manufacturing space, but they are forming very, very close relationships with the companies that do the manufacturing. And I think it's probably fair to say that if you want to compete in high-tech industries, and that's where automotive is moving, those companies are probably have to pay a much closer detail to their supply chains and the semiconductor industry.
Thank you, Andy. I agree with that. In addition to a lot of these other exciting changes we've talked about, one interesting one has recently been all about ChatGPT and generative AI. Does generative AI mean good news for the semiconductor industry? And what could we expect?
Wow. I think it's probably fair to say it's very difficult to forecast the medium and long-term impact of a disruptive technology. And I think back to when mobile phones were just starting out, the size of these things. And people say, this is great, we can now talk to each other on the move. And I don't think anybody visualized within 20 years would be holding a handheld computer that could almost talk to us with ChatGPT. So when you have a disruptive technology, I think it's very difficult. Maybe it's difficult for humans to kind of visualize. We tend to think in linear steps. We don't think of completely transformative things. And I think AI and ChatGPT being an example is a completely transformative technology, and it's almost impossible to kind of visualize where that's going to take us. It's got a couple of interesting aspects. So firstly, it will be a driver of the semiconductor industry. It will enable new companies to exist that are designing the chips that create the AI. There's no doubt about that. So there's going to be a massive shift of companies maybe pivoting from their existing design operations into designing AI chips. There'll be fabrication of these chips. There'll be new architectures. Fabricating a single chip with, at the moment, I think we're up to about 10 billion transistors per chip. I think there might be one that's 100 billion. But at some point, we're going to need to think about how do you fabricate chips with 1 trillion transistors, and we might need to re-architect how the fabrication of those things are done. So there's some interesting challenges ahead. But there's also the use of AI in the semiconductor industry itself. And could AI be designing things for us? And I've heard from a lot of colleagues that if you ask AI to design some Python or some VHDL, it does it frighteningly well. So it is starting to move into the space, which has predominantly been the preserve of human intellect. It is moving into that space rather rapidly and at a frightening pace. Some interesting things where we've been working on in the Catapult, actually, we've been using AI to accelerate simulation and modeling. So if we're trying to design a new system, we quite often have to simulate it and model it. And we might have to simulate, 200 different scenarios, very time consuming, to try and work out what the optimal scenario is. And we're starting to work with AI to see how do we speed up that process, and can we use AI to select the best scenario much, much faster than a human can. And actually, it turns out to be very effective. So there are definitely some positives in AI, and I also think there are probably some cautious traps that we need to avoid. Very difficult to spot what they're going to be, but I think we need to be cautious.
Yeah, no, I agree, Andy. And the funny story I tell you, the other day my son came to me and he said, I play a little game with him. He needs to tell me what shares to invest in. And he comes to me and says, Dad, I did a quick ChatGPT search, and these are the 5 shares you need to invest in. And one of them was Nvidia. And I said, no way am I investing in a semiconductor chip. There's overcapacity. I don't want to lose any money. And guess what? It hit a $1 trillion in valuation. So maybe question to you is this valuation justified? Will we see others? Is this the way forward for the semiconductor manufacturers?
Yes, I saw that news. Nvidia hitting $1 trillion. It's incredible. On the whole, I think markets tend to be very good forecasters of the direction of travel, because there are pressures on getting the share price up, and there are equal pressures on there are pressures on buying and there are pressures on selling, if you like, in markets. So markets tend to be quite efficient predictors of the future capability of a company, so certainly in the small, short to medium term anyway. So clearly the market analysts have seen Nvidia has that potential, but also, as I mentioned earlier, kind of the disruptive nature of artificial intelligence means that it's very, very difficult to completely accurately forecast what that market's going to be. So I suspect that the valuation is a true reflection of where the analysts think it's going. It's and also the other thing, perhaps just to kind of reflect a little bit, is when we've seen other sort of transformative industries come along, sometimes you get a bubble, but equally there tends to be a long-term trajectory. And I'm thinking perhaps, going back to the sort of 1990s and the internet, and clearly again it was a transformative industry, and Bill Gates was interviewed endlessly about the internet, and people were still struggling to get to terms with exactly what this new internet was going to do. And yet it really has transformed our lives. It's transformed industry. We don't think about it anymore. It's just secondary nature. But equally, the valuations did result in some early bubbles and some consolidation in the industry. So there tends to be that dynamic. And I think markets are very efficient at kind of working their way through that dynamic.
Thank you, Andy. I agree with you on that. So let's just maybe talk a little bit about sustainability. We see the world moving towards greener technologies, electrification, possibly hydrogen in transportation, in energy, and the whole, the topic of energy transition. So in this context, semiconductors play a key role. Could you elaborate a little bit how you see the semiconductor technologies contributing to this global drive towards electrification and sustainability? Also, the fact that they're also big consumers of energy.
Mm. I think you're right. I think semiconductors actually fall on both sides of the balance sheet. On the one hand, they're an enabler to get us to better sustainability. On the other hand, they're a consumer. They're consuming energy. And I think where we need to get to is on that balance sheet analogy, we need to get to the position where semiconductors are driving the sustainability model going forward. So some of the areas where they're being active, clearly, as we move away from conventional vehicles, internal combustion engines, they're producing a lot of pollution at the point of use, a lot of CO2 emissions at the point of use. As we're moving towards electric traction, semiconductors are driving that move, and in particular, compound semiconductors like gallium nitride, silicon carbide, and maybe even gallium oxide in the future will be more efficient at taking the power from the battery to drive the electric motor. That will extend the range of the vehicle. It reduces the consumption it reduces the production of polluting gases at the point of use. But also, it doesn't really totally solve the sustainability challenge because currently a lot of that electricity is being generated elsewhere in the grid by non-sustainable means. So it might be being generated by oil power stations or gas power stations, what have you. So we need to address the supply side as well. I think how we're going to do that is an increased reliance on renewable energy, solar, wind power, etc. And the slight trick there is that renewable energy sources are inherently intermittent. So you get electricity when it's windy, or you get electricity when it's sunny. And quite often, the amount of electricity you can generate when the conditions are right far exceed your ability to consume it. And I heard some statistics I think it was Scotland, could generate 40 gigawatts of power in a windy environment, but no ability to consume that level of power at the point of generation, at the time of generation. So clearly, we need to find mechanisms of banking that power, storing it, and then redirecting it to the consumer when they need the power. And that will require semiconductors to do that storage, putting the power into battery, and also taking that power out of the battery and directing it back into where it's needed and when it's needed. So smart energy grids. One other sort of example, if I may, and that is on telecom networks. Telecom networks, we experience them when we switch on our mobile phone. We connect to the radio access network. We exchange data with a base station. That data then goes back into the network via backhaul and then goes onto a server, and a server processes that data, it stores our photographs, it reroutes the data. Now, there's a couple of energy consumption issues here. The data centers use energy. About 2% of global energy is in data centers. The telecom network is about 3% of global energy requirements at the moment, and forecast to become unsustainable by 2030. So on the one hand, telecom networks enable us to communicate as we're doing at the moment without having to travel, which is on the balance sheet, it's a positive for sustainability. On the other side of the balance sheet, we're consuming energy by building the telecom networks. So we really do need to get to a smart place and semiconductors are central to this. We need to get to a smart conclusion where semiconductors are driving down the energy usage and driving up a sustainable existence.
Thank you, Andy. Maybe one question on Moore's law. Do you think in future things like neuromorphic computing or DNA computing or quantum computing, will they challenge Moore's law, or have we reached the limit of Moore's law? I know I threw this one in, Andy. If you want, we can skip it, but up to you.
And that's okay. We can address Moore's law. So I guess Moore's law specifically referred to the observation that the number of transistors on a silicon chip was doubling every 18 months. So either you had twice the functionality every 18 months, or you had half the cost every 18 months, or some sort of compromise in between the two. We're certainly getting to the point where it's not going to get any smaller. I mean, I think we're down to 3 nanometers at the moment. There's a roadmap to 2 nanometers and maybe 1 nanometer. So clearly the acceleration has slowed down enormously. Now, I think there are other ways of tackling this. I mean, effectively, nobody really cares how many transistors are on a chip. What they care about is the functionality of the chip. Can that chip do twice the functionality within a reasonable footprint and within a reasonable energy and power envelope? And I think there are a number of ways that we can address Moore's law. One is by going to chiplets. So instead of the chip getting bigger and bigger and bigger, and this is the kind of the point I mentioned earlier about, you can have 10 billion transistors on a chip, but maybe you can't have 1 trillion transistors on a chip. But maybe what we can do is go to chiplets, whereby we have functional blocks, each with 1 billion transistors on, and we hook them together in different ways to get up the functionality. So there are some ways that we can approach Moore's law in that respect. Ultimately, when it comes to the functionality of the chip, it's doing millions of calculations. Chips are very good at arithmetic, multiplication, all this sort of stuff. And there are very advanced algorithms which are used to do calculations, to simulate weather conditions or to do encryption and that sort of thing. And I think quantum computing will accelerate that. So it will have certain functional blocks whereby it can do encryption and decryption. Maybe it can do weather forecasting, weather modeling. And I suspect that the architecture of the future is going to be a fairly similar to computer architecture at the moment, where you have a standard microprocessor and memory, etc. And instead of having a video card plugged in, you'll have a quantum card plugged in that will offload some of the quantum computing attributes and functions.
Thank you, Andy. Maybe last question from me. You already covered this briefly, but I just wanted to ask you, how do you see the competitive advantage of UK? And in particular, what is the Catapult doing to enable that?
I think we probably recognise that, we talked earlier about the investments that are going into the US and the EU, and the fact that the UK has to be selective and strategically, how we recognise our strengths and play to those strengths. And I think we've recognised that the UK has strengths in semiconductor design and IP, research and development, and compound semiconductors. So kind of three core strengths to build on. And also those kind of core strengths don't necessarily compete with the big investments which are going on in other places in the world. So it kind of gives us a nice niche to complement other investments, if you like. Now, how we should build on those is actually the subject of a piece of work which is going on at the moment. The Department for Science, Innovation Technology has commissioned some semiconductor infrastructure studies, and the Catapult is playing a leading role in these studies. We're assessing the investment opportunity to invest in potentially 4 infrastructure investments. So one is a silicon at prototyping level, one of them is advanced packaging, one of them is compound semiconductor foundry, and another one is support for design and IP. The piece of work is actually being led by the Institute for Manufacturing at Cambridge University, and the Catapult is playing an active role in supporting them. But we're consulting very heavily industry and academia in the UK with a view to making some recommendations later this year.
Thank you, Andy. That's really very helpful. Andy, thank you very much for such an interesting discussion. I mean, your knowledge is exemplary. I mean, you're a true thought leader in this. So thank you to you, and thank you for everybody for listening in. I was in conversation with Andy Sellers, Chief Business Development Officer with Compound Semiconductor Applications Catapult. Thank you, Andy, once again. Stay tuned for such interesting episodes on Disruption Dialogue.
Thank you.
Thank you.
Thanks for tuning in. If you want to know how you can navigate and thrive in this disruptive era, subscribe to Disruption Dialogues on your go-to podcast channels and stay tuned for more interesting episodes.